Okay, so real quick, let's zip through this. So the imaginary unit I is defined as what? Square root of -1. There you go. I squared is equal to -1. Okay. If A and B are real numbers, then any number in the form A plus B times I is called what? A complex number. Complex number. And what do we call? Okay, well, what's the real part of the number 18 plus 4i? 18. What's the imaginary part? 4. Okay, how about this number right here, the number 1? Identify what are all the sets that belongs to? Is it pure imaginary? No. Is it real? Is it complex? Yes, all numbers are complex. Is it a non-real complex? No. There you go. Okay. Square root of -16 is 4i. Good. And the important thing there is the negative inside becomes an I outside. Okay, now what about the powers of I? How do we deal with I to any power? Right, now we can do it like we went through a couple of patterns, but the easiest way to do it is to write it in terms of I squareds, right? So I to the 30 is equal to I squared to what power? The 15th. And what's I squared? Okay, so I'm getting -1 to an odd power. So what's the answer? -1, right? -1 to an even power is 1. -1 to an odd power is -1. Okay, so that's how we deal. Even powers of I are super easy. Odd powers of I are, not much harder. An odd power of I, we're going to write it as it's going to be the biggest possible even power of I times I, right? I to the 25th is I to what power times I? Okay, there you go. I to the 24th times I, right? Then all we got to figure out then, so we know we're going to get this leftover I in our answer, but I to an even power is either going to be -1 or +1. So our answers are either going to be I or -I, right? We just have to figure out which one. Okay, so then I to the 24th is the same as I squared to the 12th times I, and that's equal to -1 to an even power times I. What's -1 to an even power? 1. So the answer is I, exactly. Because that whole thing is equal to 1. We have a little trick for that too. Remember, there's a little trick to set this thing up. 25 over 2 equals 12 and 1/2, right? So that 12 is going to be the power of I squared, and the 1 corresponds to the extra I. See how that works? Just an easy way to kind of just check that. Okay, give me thumbs on that. Is that good? Okay. All right. I gotta, I gotta fix an attendance. It's a school activity. Okay, so then what about Adding and subtracting complex numbers. Adding is dead simple. We'll just do a subtraction problem to review because it includes both. What do I have to do to subtract these two? Good. We distribute the negative, right? So there's nothing to distribute here, so I just get 5 plus 7i, and then when I distribute that negative, I get minus 8 plus 5i. Add like terms, exactly. So we've got the numbers, 5 minus 8 is negative 3, and then we've got the I terms, right? 7i plus 5i is plus 12i. There you go. Okay. Good, good. All right, multiplying. What do we have to do when we multiply? Distribute. Yeah, we just distribute one to the other. And we're treating the i's just like x's, just like we did when we added and subtracted, except when we're multiplying, we're going to get maybe some I squareds. And what do we do with the I squareds? Turn them into -1. Exactly. Okay, so let's go through this then. So if I distribute the -2, I'm going to get -2 times 2 is -4. -2 times I is -2i, right? If I distribute the 2i times 2 is plus 4i, and 2i times I is plus 2i squared. And again, the I squared, exactly, it's going to turn that into a -2, right? And so we end up with then, if we rewrite that, we end up with, yeah, -4 minus 2i plus 4i minus 2. And then we just add up like terms, and we're going to get -4 minus 2 is -6, and -2i plus 4i is positive 2i. Okay, no biggie. Okay, so what about this one? The numbers 6 plus 5i and 6 minus 5i, which differ only in the sign of their imaginary parts, are called what? Say it again? Yeah, complex conjugates. Yeah, that's the definition. So anything in the form, whoops, anything that fits this form complex conjugates would be A plus BI and A minus BI, which we could write as A plus or minus BI. Okay, that's the definition of complex conjugates. Okay, and they're important because when we're dividing out complex numbers like this, we have to multiply the numerator and the denominator by what? There you go. We got to multiply it by the complex conjugate of the denominator. So we're going to multiply both by 3 plus 2i. Okay. Is that ringing a bell, Caleb? You've done some of that, right? Oh, you haven't? Okay. Okay. Okay, so let's look at an example. Here's an example we can do. So we've got a quotient of complex numbers. I've got it, on the bottom I've got a complex number with both a real and an imaginary part. So what I have to do then for this guy, because of what's on the bottom, I've got to multiply both the top and the bottom by 8 plus I, the complex conjugate of the bottom, right? Everybody see that connection there? These are complex conjugates. And I got to do the same thing to the top. Okay? So I'm going to remind you about a little something here. When we multiply complex conjugates together, we always get the same result. Let's just see what happens. If I multiply A plus BI times A minus BI. We did this the other day, but I'm going to do it again because I think you were gone. If we distribute, I'm going to get A squared minus ABI plus B times I times A, which we'll write as A times B times I, minus B squared. BI times BI is B squared times I squared. And look what happens. Those guys cancel out, don't they? Those are like terms, right? Anybody see that? And so I just end up getting A squared plus B squared. That's always true. When I multiply complex conjugates, I always just get A squared plus B squared. Okay. Put a box around that. So when we multiply these out, it's really easy to do, right? What if I'm multiplying the bottom here? A is what? What's B? No, okay, 1, right? Because we're going to add it and subtract it. See what I'm saying? So on the bottom, we're just going to get 8 squared plus 1 squared. Easy, right? Now on the top, we just have to distribute. If I distribute the 4, I'm going to get 32 plus 4i. And so we end up getting on the bottom, 64 plus 1 is 65. On the top, I get my 32 plus 4i. And then all I've got to do, we need to write our answer in standard form for a complex number. So well, they went away. When I multiply the complex conjugates, notice what happens. When I multiply the complex conjugates, the I terms all go away. Which one? That's a 1, not an I. Mm-hmm. Oh, yeah, right. Exactly. That's going to become a -1, which makes that a plus. There you go. Yeah. Okay. Right. So then we end up, and we want to write this as separate real parts and imaginary parts. So we're just going to split that denominator into 2 separate fractions. Right. So we'd write this as 32 over 65 plus 4 over 65 times I. And now it fits our pattern. Okay, see that? Okay, give me thumbs. Good. What aren't you sure about, Max? Say it again. Where on the? Oh, well, it was, right? So we multiplied. This is what we started with, right? So we multiplied by 8 plus I over 8, 8 plus I. No. No, because the complex conjugates, I see what you're saying. Complex conjugates, the real part is the same. It's the imaginary part that changes sign. See what I'm saying? Like if we go back to that last page, look at this. Look right here. So the numbers 6 plus 5i, positive 6 plus 5i, and positive 6 minus 5i. The 6 is positive both times, right? Those are called complex conjugates. The only thing that changes is the sign of the imaginary part. Okay? Does that make sense? Okay. All right, so now graph the complex number in the complex plane. Where would I graph the complex number -6 plus 7i? Yeah, right. And the whole point here is that we're graphing the coordinates in the complex plane are ordered pairs of the form AB, right? Where this is A plus B times I. So A is equal to -6 and B is equal to 7. So we'd go back 6 and up 7. And there it is. Okay, make sense? Okay. All right, did we? I think I got everything on that last page. Yeah. Okay, find all complex number solutions. So what are we going to do? There's only one step there. What do I have to do? Say it, the top one. What do I do? Square root both sides, right? I'm just trying to isolate x. There's only one step in that case, right? So I can point to a single x, so I can isolate it by just inverse operations. All I've got to do is square root both sides. So I end up with x equals, what do I always have to do though if I'm square rooting both sides? This is what people sometimes tend to forget. If I'm square rooting both sides, right, I'm doing this. What does that mean I always have to do? I'm doing this to get rid of that x squared. Let's try a quick example problem. What if I have x squared equals 4? If I square root both sides, what do I get? Plus or minus, right? Because -2 or +2 squared are both equal to 4, right? Make sense? So I got to put my plus or minus, and then I've got the square root of -100. Exactly, right. And so, and that's what we do. We turn this into plus or minus the square root of 100 times the square root of -1. And what's the square root of 100? 10. And what's the square root of -1? That's I, right? Good. But we don't probably even need that step. We can just skip that step because we know that if I have a negative number inside a square root, that's always just going to become an I outside of the square root, right? So those are our two answers right there. X equals plus or minus 10i, okay? Find all complex number solutions. Okay, so same kind of thing, right? It looks like the same problem. The only issue here is this time it's not a perfect square, so it's a little bit tougher. We're going to square root both sides, same as before, and we're going to get x equals plus or minus the square root of -99. Well, we already know that negative inside is going to become an I outside, right? But we still got to deal with the square root of 99. So let's make a factor tree out of 99. We could do 30. We could do not. Oh, I see what you're saying. So you mean 9 and 11, right? And 3, right? Okay, but what we probably want to do, and that's going to work. What we'd like to do is put a number here that's going to be a perfect square, if possible. That's going to break into only a couple. That'd be 9. Good. So we can break that up into a 9 and an 11, right? And then the 9 we like because it's a perfect square, and we get a couple of 3s out of that, and we're stuck with a single 11, right? So the square root of 99 part is just going to become, by couples go out, singles stay in. We had a couple of 3s, so we get a 3 out, and we had a single 11, so we get an 11 in, and that's it. Plus or minus 3 times the square root of 11 times I, because the square root was negative. Okay, questions? Good? Okay, how are we going to solve that equation? It's in standard form, right? I cannot isolate x because I can't point to a single x. Could I factor it? Are there magic numbers? What are they? 4 and 3. Yeah, they multiply to 12 and add to 7. So this is actually one that we could do by factoring, right? could do this one by factoring. I could break it up into x plus 3 times x minus 4 equals 0. And then by the zero product property, x plus 3 equals 0 when x is, no, negative 3, right? I'm going to set that factor equal to 0 and solve. And so I get negative 3. Here, if I set that one equal to 0 to see what value of x makes it 0, I get 4. And I probably could have just done that in my head, right? Okay, so those are my answers. What if I didn't see that? What's my other option? What if I didn't see the magic numbers? Oh, yeah, you're right. Sorry. Plus, should be a plus, shouldn't it? So that's a, yeah, so that should be a negative. Yeah, you're right. You're right. My mistake. There we go. Okay, good. So those are the solutions. But what if we didn't see the magic numbers? There's another method we could use. What's that? Quadratic formula, right? We can always use the quadratic formula. This is what we did is better. It's quicker, much quicker and easier. But we could use the quadratic formula. We see A is 1, B is 7, C is 12. And we know, okay, you guys remember the quadratic formula? X equals, you remember seeing this? What is it? Negative B plus or minus B squared minus 4AC divided by 2A. There we go. So now we just plug and chug. If we plug that stuff in, so negative B would be negative 7 plus or minus the square root of B squared. Well, that's 7 squared minus 4 times 1 times 12, all divided by 2 times 1 is 2. Well, that's negative 7 plus or minus the square root of 49 minus 48. That's 1, right? And so that's just 1, right? Square root of 1 is 1. And so we end up then with negative 7 plus or minus 1 over 2. Well, now we can do this we can just take the plus sign to get one answer. If I take the plus sign, x equals negative 7 plus 1 is negative 6 over 2. Well, that's just negative 3, right? If I take the minus sign, negative 7 minus 1 is negative 8 over 2. That's equal to negative 4. Okay, so we can get it that way too. Yes, sir. Mm-hmm. Yeah. Yeah. Yeah, I wonder. Okay, so how about this one then? Well, here's one where we definitely cannot find magic numbers that multiply to negative 2 and add to 2. So this time we have to use the quadratic formula. So what are we going to get here? So we know A is 1, B is 2, C is negative 2. So what I would recommend is always start off by writing down the quadratic formula and then plugging and chugging, right? So we get negative B, that's negative 2, plus or minus the square root of B squared minus 4 times 1 times negative 2, all divided by 2 times A. So 2 times, well, I guess I didn't write it down, did I? I just started plugging it in. Oh, well, okay. Here's the, if you want to refer back to the formula, there it is right there, right? Okay. So there's our formula. Here's our new values of A, B, and C. And so we just plug those into our formula, right? And now we have to simplify. So we get negative 2 plus or minus the square root of, let's see what happens in here. If we take all the stuff in here, what's going to happen? Well, I see one thing going on. If I multiply a negative times a negative, they become positive, right? And so we're going to get 4 plus 8 is 12 inside. All divided by 2. Okay, so we got to simplify the 12. If we take our 12 and we make a factor tree, is there a perfect square that divides into 12? 4. There we go. Good. So we want 4 and 3. We like 4 because it breaks into a couple of 2's. And we got a single 3, right? So our square root part then, we've got our -2 on the top, plus or minus. The square root part's going to give me, I had a couple of 2's, so 2 goes out. I had a single 3, so a 3 stays in. And then the whole thing is divided by 2. Now this time, I can't combine the numbers on the top because one of them is an integer and one has a square root, right? So they're not compatible. They're not like terms. So I'm going to split this denominator up. And we're going to get -2 over my common denominator of 2 plus or minus, there's my plus or minus, 2 times the square root of 3 divided by my common denominator of 2. Everybody get that? Okay. And then now finally I'm going to simplify. So Caleb, what can I do? What is -2 over 2? Okay. What can I do to this one? Square root 3. Good. I can cancel the 2's. And so I end up with plus or minus square root of 3. So those are my 2 answers, right? Could I have gotten there more easily? Well, one thing maybe you saw is I could factor a 2 out of the top and cancel it. But to me, that just seems like it's harder to do, right? Seems like it's easier just to split these up and simplify them independently. Okay, because and I'll tell you another good reason to do that. Sometimes one of the fractions will simplify and the other one won't. Okay, give me thumbs. We good? All right. Okay, same kind of thing, only no magic numbers. Another quadratic formula problem. So this time, A is 1, B is -6, C is 25. So let's start off with the quadratic formula. X equals -b plus or minus square root b squared minus 4ac divided by 2a. Okay? If we plug in our stuff then, -b is what? 6. Good. Plus or minus the square root of 36. Good. And we get that from -6 squared, but we don't want to square a negative. We always just square the positive, right? We're going to ignore that negative. Ignore that when squaring. So we get 6 squared minus 4 times 1 times 25 all over 2 times 1. So that's giving us 6 plus or minus the square root of what's going to be in here. So this is all going to give me inside the bubble, I'm getting 36 minus 100, right? That's -64. All divided by 2. There we go. So we get 6 plus or minus, and let's just take a look at this part right here. We know that the square root of -64, the negative is giving us an I, and the 64 is giving us an 8, right? So we're getting 6 plus or minus 8i all over 2. And now we're just going to split this thing up again like we always do. Unless we can add those numbers up there, right? Like in the first example. So our final answer then is going to look like 6 over 2 plus or minus 8 over 2 times I, right? There's my I, and I'll put the I after that second fraction. And why are we doing this? Because we want it to look like standard form, A plus B times I, real part and imaginary part separate. So then we can reduce those fractions, right? We're going to get 3 plus or minus 8 over 2 becomes 4I. Okay, good? Those are our answers. Okay, give me thumbs. Good? All right. Okay, now last couple things are just using the discriminant, right? Easy stuff. So using the discriminant, that's just the part under the square root. Yes, sir. Yeah, you bet. So the discriminant is the part under the square root in the quadratic formula. So that's just the part right there, right? The b squared minus 4ac part. So if we plug in our numbers, well, actually, we have to put this in standard form first, right? Because in order for us to do this, we have to start with a quadratic equation in standard form. Good. Okay, so first thing we're going to do is we're going to change this over. We're going to move all this stuff over to the other side, aren't we? Because we want to have a be positive. So we'll add 5x squared to both sides. We'll add 2x to both sides. And then we've got it, right? Then we've got our quadratic equation in standard form. And so now we can see that a is 5, b is 2, c is 5, and we can calculate the discriminant. So we're going to get our discriminant equals b squared, so that's 2 squared minus 4 times 5 times 5, right? It doesn't ask us for the value of the discriminant. We don't really need to know the number. We just need to know if it's positive or negative. Well, what's that going to be? 4 minus this big number. It's going to be negative, right? It's definitely going to be a negative number. And so if it's a negative number, if the discriminant is negative, what does that tell us? Let's review that. So if the quadratic formula, let's just look at this one more time. So this is the quadratic formula, right? X equals negative b plus or minus square root b squared minus 4ac, all divided by 2a. Well, where are the imaginary numbers going to come from? Imaginary numbers come from having a negative number under a square root. So we know if b squared minus 4ac is negative, meaning it's less than 0, then we're getting 2 imaginary solutions. Right? Now, on the other hand, if our discriminant is positive, well, then I'm not getting any i's in my answer, right? And I'm getting 2 solutions, one for the plus and one for the minus. Just like I got two imaginary numbers when it was negative, one for the plus and one for the minus, right? Exactly, yeah. Okay, right. And then if it's equal to 0, we get 1. So in this case, we know the answer is too complex, right? And then finally, we got one last problem, and I think we can get it here. We can calculate the discriminant really quickly. We got to put this in standard form, so we just write it as we've got negative 2x squared plus 2x plus 3 equals 0, but a is not positive, so we'll distribute a negative through, and we'll get positive 2x squared minus 2x minus 3 equals 0. So b squared minus 4ac is negative 2 squared, but we'll make it a positive 2 squared, minus 4 times 2 times negative 3. Look what happens. Negative times negative is positive. We know we're getting a positive number, which means we're getting two real solutions. Exactly. We made it. All right. Good work.